So afternoon, we'll go through some of the labs. Okay. In order to get some hands-on exposure to the segmentation models, you can use this package called Segmentation Models PyTorch. Shortly, it's called as SMP. Segmentation Models PyTorch. So this is the GitHub link. I'll share this GitHub link in the chat. Huh? This is segmentation. Okay. So this would be a recommended GitHub to explore. So what does this has? The main features of this library is that you could implement a segmentation model with few lines of code, because they do some high level abstractions and expose all the underlying detailed implementations as high level APIs. And with just couple of lines, you can create a So what I was saying is, for the hands-on labs, we will use this GitHub repo called Segmentation Model PyTorch. It's also called as SMP for short. The main features of this library is that they have done the high-level abstractions, and with like few lines of code, we could create a segmentation model neural network, and you could do training on your custom datasets. Okay. That is the main key points of this library. They support all different types of encoder-decoder model architectures. Uh, Most of the segmentation models are follow the encoder-decoder pattern. So one of the examples is the unit. Unit is one of the most widely used segmentation models. Mask-CNN, in the other hand, is not an encoder-decoder model, whereas unit is actually an encoder-decoder model. So as I explained in the morning, the encoder takes in images in input and then encodes them into a latent image embeddings. And then the decoder takes these latent image embeddings and reconstruct an output image. So input image will be a normal RGB image. Output will be a binary image like this. Okay. Which means the decoder's job is to take an image embedding and reconstruct this binary image. It has to come back to the image space from the embedding space. They support 800 plus pre-trained convolutional based and transformer based encoders. As I told you, there are two main families of computer vision image encoders. The first generation is basically the convolutional neural network based. Then after this transformer era came, all of the other latest advancements are transformer based. Then this library also supports the popular metrics and laws. So today morning we saw the dice laws, and there are other different types of losses, but the most frequently used is a dice loss. They also support ONX export, .script export as well. Okay. So how do we use this? We use this by installation, by pip install segmentation model PyTorch. And you can just, with these two lines of code, you can create a unit segmentation model. Okay. So that's the simplicity of this segmentation model PyTorch library. Okay. You could either go through this documentation page, or you can go through this README file as a reference and use the segmentation model PyTorch framework in your projects. Okay. These are the some comprehensive documentations are available also. Think first step would be an installation, right? So this is the typically this is how we would install this segmentation model PyTorch. It is available as a pip package. Yes. So let's say if I am opening a new notebook, so let's just change my runtime to GPUs. Okay. So the library is installed. Next step is would be a quick start. So in this a segmentation model can be created using this simple one-line command. So it says import segmentation model PyTorch as SMP, and this SMP I am calling the unit. So the other types of model that are supported in this library or even in this link. Yeah, you can see here, right? So you have unit plus plus, MANet, eblab, v3, segformer, all those things. For the demonstration purpose, we'll use unit. So in that, you need to specify these parameters. It says what encoder should I use, right? So in here we have used ResNet 34, but there are other types of network also. Like if you are targeting a low compute environment, probably you can select mobile net, or you can experiment with more advanced encoders like efficient net. So these are nothing but your CNN models. So they also support transformer based encoders as well. Okay. So for that, probably segformer is actually a transformer based encoder. Okay. So instead of saying, okay, so this is model architecture, sorry. In order to get a table of what are the encoders available, you can come here. These are the different encoders. So as you can see, right, mixed vision transformer encoder. These are all VCNN based encoders. All of them are CNN based encoders. SNET, GG, efficient net, efficient net. Most of them are CNN based encoders only. Let me see if there are some other networks here. Darknet. So this has a lot many. Here also most of them are only CNN based encoders. Only in the model architecture they have certain transformer supports like segformer. Okay. So okay, coming to this encoder now. We also have to specify what are the encoder weights. So there might be these encoders are trained on different data sets and you can use those pre-trained weights as an initialization. Okay. So the popular pre-trained weights are ImageNet. So ImageNet is an open source dataset and this ResNet 34 was trained on this ImageNet. So what they are doing is they will remove the last few layers, okay, and then whatever the embeddings that is coming from the after this convolution layer, those embeddings are then used as an input for those units. Okay. So then the specified. Yeah, the spec 34, how do we know we have to use any? Yeah, the default is ImageNet. Probably they have explained it in the documentation. Encoders, mostly it's weights is ImageNet. Do they have other types of? Yeah. So here you have, right, you have three options for a SNET. 18 you have three types. ImageNet, SSL, SWSL. Now what is SSL and SWSL that we need to find? Pre-trained weights. Uh, okay, SSL, I'm guessing it should be self-supervised learning. Okay, and probably SWSL is another variant of SSL. Um, they have been recently added. Now, for example, REST Next, which is a improvement on the RESTnet. That one has ImageNet weights. It also has some Instagram weights, which means Instagram is another type of data set which probably contains all of those Instagram reels and images like that. So all are like internet scrapped videos. Mm, mostly it's ImageNet only. I think you don't have to worry too much about the weights. You just most probably have to use the ImageNet weights. Um, then probably this is important based on your use case. Uh, the input channels changes based on whether your input images are grayscale image or color image. If it is grayscale image, then your channels are just a single channel image. If it is a color image, then it will be three channels. Then what is your data set target is like how many classes the data set has. So in this case, there is three classes, I believe. So that's why they specified as three. Okay. Then it's a quick start. Classes. Like these are the classes. Yeah. Yeah, for that we need to look at this full implementation example. Okay, so let's open this collab notebook. So this says train pets binary segmentation on Oxford pets. So Oxford pets is another data set which is similar to the ImageNet, and it contains only images of pets, cats and dogs. This is another sort of a learning data set. So it has images of different types of breeds of dogs and cats. Okay, it's they also have bounding boxes, and they also have segmentation map of these images. Now the task is, can we build a segmentation models that can be trained on this Oxford pet data set and then able to accurately predict the mask of this pets. That's what they have demonstrated in this notebook using segmentation model PyTorch library.
Between a human or a mannequin, because we'll be using edges and features, right?
Mm-hmm.
And they give you differentiate.
Yeah, if your train a model and if a data set contains real human beings and a mannequin, they would be able to identify it because the mannequins, if they are dressed up, I think it's a little bit difficult.
They have similar features,
yeah.
right? Similar edges. So,
Yeah, but I hope if you have sufficiently good representative examples, they should be able to. And most of the mannequins are white skinned. So if you give a Asian skin or dust skin thing, it will definitely tell you it is.
let's say if I want to see, yeah, this.
Sorry?
I'm just thinking out. If there is a mannequin, it will be there primarily house next to the shop, on the front wheel, on the street, or inside, which is not seen. So it will depend on what we are trying to capture and where we are trying to capture. No, I was thinking from if say for example I have an autonomous car that is like here in India, and if you go to Indian streets, there are so many mannequins which are on the footpath, right? So how does your model differentiate between a human being and a man? Footpath, there will be still.
You're not driving on the footpath, but
Your car will stop saying that they will move. But I think there can be ways out to look at. We can filter out some of those features, moving, not moving. Yeah, how do you from that point of view? No, no. I'm saying there can be ways to, filter out some of that data, that whether it is on the path, how inside, outside. No, I mean, even if your trees, your cars parked, on the way with the road, they're also stationary. They're also away. You're not driving, on them, right? But your still model needs to identify all of them. So I was just curious, because they share similar features and edges. I was just wondering if it is.
yeah, that's a good, interesting case because when they are testing these self-driving cars, probably they just put a mannequin in front of the car and see whether they are stopping. So which means they should be trained to stop if they see a mannequin coming in front. But if it is on the pavement, that
आवाज आ जाती है तो मतलब पता चल जाएगा कि मतलब अगर उसने हल्ला किया अगर हल्ला नहीं किया तो नेट समझ
oh yeah. So this is happens in these highways, right? So they keep like a real looking police guy to scare. It's like a scarecrow kind of thing, right? Yeah. Yeah, yeah, it's real. When you go near just 3 meters away only, you will know that that is actually a cutout. Probably they came up with some really creative way to control. Uh, okay, so this is full example of how to train an image segmentation model onto this. Okay, let me stop this session. So what they're saying in this is that the task is to classify each pixel of an input image. So what is this called as? Morning we use some term, right? What is the terminology to describe the classification of each pixel of an input image? Yeah, but there was one more term like we used to. So dense prediction. So that's basically what they do, right? So we have to basically classify each pixel. So it is the classification and is not happening at the image level. It is happening at the pixel level. Okay, each pixel you have to tell whether it is a cat or a dog or is background. That's why there is three class: cat, dog. One pixel it will either say 0, 1, 2. Like, sorry. Oh, based on one pixel, how it will? No, no, no. It cannot. It's not looking at pixel by pixel, but give the white cat to it. Yeah, it can get confused. It can get confused, right? Hmm. See, this is how it works actually. So you give an image, it goes through the encoder. It basically has an image embedding. Then it reconstructs the image actually. So it is not taking that input image, going pixel by pixel, it's cat, dog, or cat, dog, cat, dog, cat, dog, like 1 million times. It doesn't do like that. That's like, I don't know how to call that, but yeah, but how do we do the final goal is to do that. So the final goal is to every pixel should say this belongs to cat or dog or background. But one of the way is to go pixel by pixel and say it is cat, dog, or background. But is that the way? It's possibly not possible to do that, and that's why we have this technique. So what are we going to this is so we have a data set and we also saw in the first day what are data sets and data loaders in PyTorch, right? So we will be using those concepts. Then we will be using training and validation and test routines. Okay. This is fundamental for PyTorch based deep learning modules. The user or the developer has to define all these training, validation, and test routines. Then we will use IOU metric as the quality measure of the segmentation. So you could use IOU or you could use dice loss. So dice loss and IOU are sometimes interchangeable, okay, because they are almost same. And then we will look at the results visualization. So these are the four things that we are going to see in this notebook. Okay, so the prerequisite is that you could have a good familiarity with Python, have some basic understanding of what PyTorch is, and some experience with neural networks. Okay. The first step is to pip install the segmentation models PyTorch library along with the other library called augmentations, which will be used for data augmentations. Okay. So what are all things we are importing? We are importing PyTorch, we are importing matplotlib. There is also one more library called PyTorch Lightning, which is a wrapper around PyTorch. Okay, so you remember, right, this TensorFlow and Keras. So Keras is a wrapper around TensorFlow to do some level of abstractions like that. Similarly, the PyTorch area also, some people develop some wrappers around PyTorch. And one of the popular wrapper around PyTorch is called PyTorch Lightning, which means that you could just do a training with few lines of code. You could just say model.train, similarly how you do it in Keras. Okay. So all those low level coding will be done for you, and then you just have to write some high level API calls. So that's PyTorch Lightning. Then some other modules that is required to define or specify your training parameters, like the learning rate scheduler, uh, data loader, etc. Okay, now let's run this. Should I share this notebook? Okay, this is okay. Okay, so then in this, we are using a predefined data set for simplicity. The data set actually reads pairs of images and mask. Okay, so we have images and we have their corresponding mask as their labels. So here mask is our labels from the disk and return sample dictionary with keys, image, mask, and other relevant and others not relevant for this example. Okay, probably we only need this, but this data set contains additional information which we do not want, which we will not be using it. Okay. All right, that's it. So this data set, Oxford Pet data set, is already part of this SMP package, which is under the data sets. So I am importing the data set. Okay. Now I am downloading to my local. So you're also running this notebook, or okay. So you're done at home. Okay. See, Ultralytics also have segmentation models. Yeah. These models are see. So these models, suppose if the Ultralytics model's performance is not as good as these models, then you need to train both frameworks, compare their performance, and select models. So in deep learning or any machine learning, it's a very empirical field. It is very difficult to tell in advance which model is the best. Um, so that's why like you try like 3, 4 models and select one of the best one from them. Not exactly the same thing, but you also have all segmentation support in Ultralytics. So if we go to Ultralytics docs, they do have so they do have models. Yes, task, right? In the task, you see they have detect segment also. So you could use segmentation models. So you got so you have YOLO 26 seg. So you also have YOLO 26 that supports object detection also. Yeah, mostly YOLO models. Let's see what are the models available. Right, George. Yeah. See I think from YOLO V level onwards, it supports segmentation also. See, if you go to these models, you have from V3 all the way up to 26 and various other models also. Then in here, they will see what are the supported tasks. For YOLO V11, you see it suppose YOLO V11 means without any suffix, which means it is an object detection. If you have a suffix like seg, which means it is segmentations. Post means post estimation. OBB means oriented object bounding. CLS means classification. Okay, but if you look at V10, I'm not sure if it supports segmentation. See, it does not support. It has only deduction. It has only deduction, right? So if you want a segmentation model within Ultralytics, you have to use YOLO V11. Let's check whether V12 has segmentation support. Yeah, it also has segmentation support. You could use V11, V12 or 26. Either one of these three you can use. Okay. So now if I see, I have downloaded the images. Okay. All right. So then here we are Hmm? Mm, yeah, I think so. No, it doesn't use transformer. So transformer is mainly this real-time detection transformers. Only those are all transformer-based object detection. So here we are splitting the dataset into train, validation, and test. Then we are just printing out the size of each splits. Then we are creating data loaders for train, validation, and test. It's so the in train we have 3,312 images. In validation we have 368 images. In test we have 3,669 images. Now just let's take a quick look at few of these examples. And this is how the image looks like. This is the input image. This is its corresponding binary mask. Okay. The task of the model is to predict this mask as accurate as possible to match this ground truth mask. Okay. So these are all being human labeled mask. Someone has sit and they have drawn a mask around this cat and they have created this. Okay, it is then using this we have trained the model. Suppose if you have a new custom data set and you have images and you want to segment a certain object within that image, the first step is to generate this mask. Yes. So that we saw in the last class, right? We go to see that.
Sir, one question on this one. I'm audible?
Yeah, I see somebody raised hands. Yes, Santosh,
Yes, sir. So can you go back to the collab
you have a
notebook?
question?
Yes, yes. I can. Can you hear me, sir?
Hello?
Yeah. Can you hear me? Hello?
Who is moved? Oh, okay. 1 second, 1 second.
Yeah.
Can you speak now?
Yeah. Can you hear me?
Yes, yes.
Yeah. So if you just go back to your collab, um, so the first question about that human-made mask, right? Which you're showing this one, okay? So this is the ground truth, right? So manually, somebody has made it, right, and kept it somewhere,
Mm.
right?
Yes.
Now, in the current example, when you have train, test, and validation data set, is this available there also?
Yes. For
Okay.
all the train test split, we have these annotations. So this is the
Okay.
dataset directory. We have
Right.
images subfolder and annotation subfolder. In images, you have train, test, and validation. So like
Okay.
this, you have these images. Then
Okay.
we also have its corresponding masks. So if I open one of this,
Right.
probably its PNG is not displayed properly, but if you load it properly into a open CV, then you will see the mask, I believe.
Yeah. So that is fine. I got the answer. The next question was that so the final comparison we will be doing against this image only, like ground truth and what our data model has found it, right? And we'll
Yeah,
find the accuracy.
yeah.
Okay. Now, if you let's say this is trained on few set of images, for example, let's say 5,000. now I have an image which is not mask. So do I need to do manually mask and then train the model again? I mean, let's say there are set of images which are not on which this is not trained. For example, we are trained with three categories. There is another one, let's say um, something like that, cat, dog, or I have a image for
If
something
you have
else.
something for what other pets we use, like I don't know.
Yeah. Okay. So I was
Okay.
asking that whether masking has to be done first and then train the model.
If it is another type of pet, let's say pigeon, you're
Pigeon. Okay,
asking
bird.
whether the
Yeah.
model can predict the mask of the pigeon.
Yes.
It
I
cannot.
mean, no. So, but I'll be providing the mask image. Like I have the pigeon original image and I have the
Mhm.
mask image also. Both are there with me. So how do I do it here, for example? Do I need to train this one?
Yes. You have to
Okay.
again
Okay.
train the model. Yeah.
Okay, sir. All right. Thank you.
Okay. That is what in CVAT we can do that. Yeah, it's a bit little tedious, but of late we have this SAM model, which makes this creating this mask is little more easier than if you want to do it uh, completely by your own. So there are some assistance available with the latest SAM actually. So that's why SAM is like a very powerful model. Yeah. Yeah. So let's say I delete all this. So you have to go to this polygon. Okay. Uh, and then this would be something like this. So somebody has to sit and draw the boundary of the person like this. Not this mask, but bounding boxes. Yeah, yeah, I think. Yeah. I even don't know how do I. So, but in latest we have this segment anything 2.0 where I can draw a bounding box around this. And then you see it is calling the segment anything 2.0 model. Yeah, I don't know the other way. That's why I told in the morning, Tesla and Karpati, they have army of data labels. Not one, two, or 100. They have probably thousands and lakhs of data labels. Hmm? So now the ChatGPT, it is trained on some billions of texts and billions of documents. There will be some lakhs of people who would have labeled this. So they should have poured some $1 million just paying the labelers. They would have hired poets. They would have hired content creators. They would have hired a lot of people who are literature experts to sit and evaluate each of these responses. and then tell them, hey, this is not the right response. They will write a response. Okay. And then they will be paid based on their labels. So these ChatGPT models doesn't come automatically from the sky, right? So they had a model. Just the GPT model alone is actually useless. GPT model is just one architecture, but it is useless without the data. And data is useless without labels. And labels can be created by humans. See, now you see, instead of creating a mask of these humans, I just draw a bounding box around it. Now the model generated mask for me. You saw that?
Yes.
Okay. Now I can even create mask for this car also. Oops, sorry. You see? So instead of taking this tool and then creating a mask like this, oh, sorry, I think it is, so instead of doing a manual way, this was there 2, 3 years back. This is like one of the ways to do it. Okay. Or there could be a little more. Yeah. See, there could be a little more. See, here there is a little more assistance is there. You see, the earlier tool, it just puts the point wherever I click. But here, I just have to roughly trace the boundary of the car, but it is able to adjust the mask automatically for me. There is a little more assistance here, you see. So this is one way of assistant. So this uses some computer vision model under that because it knows the boundary between the car and the not a car. So this is another assistant. And then the latest one was the segment anything model, where I can just simply draw a box around the car and I can get the mask instantly. So that's why it's pretty powerful. Now, if I save the mask, so how do I use this? If you follow me, I am able to create the mask instantly, right? And if I export this,
And so you have the bounding box with the coordination. How would this look like in terms of the?
That it'll look like a binary mask.
Let's say an Excel. Educated, for instance, like the goals. Just say that this is a separate object. It might be unable to annotation, but it's able to can be used. So that expert person can say that, hey, this is a goal, but whatever it is. You can say that it's still in the brain. Image is there. We don't know. There might be some objects, objects are there. And let's say we wanted to classify undefined way, unidentified objects. And let's say it's what let's say it's doctor or what could be road specialist would come and say that hey, this is let's say like stress going here.
Yeah. See, medical, it is a little bit tricky, but at least in the simple object detection, um, there are open vocabulary images like zero shot object detection. And you can just tell them to uh,
Detect objects.
yeah, detect objects. You don't have to tell what those objects are. Yeah. Yeah. So you can do right here. You can see. Yeah. See here also, if you do this segment anything, it can just scan the images and it can segment them into some meaningful groups. And but it will not tell you what those are. And you can just take that and ask somebody to just add that. So that's why SAM was created. So it's okay. Earlier they had a very better demo. I think now it has become like a more fancy thing. Yeah, that's what I'm trying to do. They have changed this and they want me to log in also. I don't have none of these accounts. Okay. Uh, oh, come on. Sorry, just give me a minute. I'll create an account and come. So let's take this image as an example, right? It looks similar to a biological cell. Alright. So earlier they used to have a very nice demo, no login required when SAM1 was released. But I don't know why they are putting so much restriction now. Okay, unfortunately, they have changed the way you can use this. Yeah, when you're trying to do this. Why this doesn't work? Oh, that guy. Sorry, what you're saying? Oh, this won't work, huh? Why? It was working till now. Okay, it's a little bit annoying, but it will look something like this. Okay, so if you have an image and this is also not playing. Okay, no. So this will be something like this. Like if I have an image and then it just scans. I didn't tell anything. It just scans and segment each and every vegetable separately into its own mask, and it doesn't know what is which vegetable. Okay, and it just gives you the mask, and you can ask some vegetable expert to tell this is carrot, this is. The assignment is just an object detection, so it will take hardly an hour to annotate. See, basically, you need to know how do we annotate and how do we export, whether you exported it in the right format, whether you labeled it in the right format. So without having a hands-on on this, how do you will train a model? Right.
Because we do this segment, we can label it.
Yeah.
And I find models which is not there, we have to do it from spreadsheet. So at that time, we can use this segment in model to identify and then labeling we can do it.
Yeah. But it, yeah, depends on the images. Okay, so then we define some training parameters. Is working, huh? And then we define some training parameters like the number of epochs. Then what is the, I'm not sure what is this Tmax, but we can look at the docs and understand. And the output class is like 1. Why the output class is 1? I'm not sure. But yeah, let's assume this is correct. Then we define the PyTorch Lightning module. For PyTorch Lightning module, we define a class like this. Okay. And then there is some initialization, which basically has how to create a model. For creating a model within the PyTorch Lightning module, we use the SMP model. So what this SMP is helping is, instead of creating hundreds and lines of code to just create this model architecture, you just call like one line of code and then you created a unit model, for example. So architecture, I'm not sure where we defined this R. Okay, hereafter only we will do. Okay, so the architecture is basically an input parameter. So instead of creating, let's say if you are creating a ResNet 34 model, you might be writing hundreds of lines of codes. Instead that the SMP is abstracting all those hundreds of lines of codes and created a ResNet model with just one line of code. Then within the Lightning module, you have to define the loss function. Then you have to create some buffers to keep all your training step outputs, validation step outputs, and step test step outputs. We will be just appending all those things to this variable, and finally we can use it for our evaluation. And then we define the forward function. In this forward function, we do have some image normalization or pre-processing defined. Then take the normalized image and then pass it into the segmentation model. And that model will return a mask. That's your single forward pass. You take an image, pass it into a segmentation model, it will give you the mask. This is your predicted mask. You follow me? This predicted mask is then compared with against the ground truth mask, and then we calculate this loss, which is nothing but a dice loss. Okay. So what do we do here? We define forward. We take an image, pass it into this function, get the mask, and that is your predicted mask. Then take this mask, compare it with the ground truth mask, and calculate your dice loss. And then this basically, if you follow this, the forward function is not giving you directly the binary mask. What it is giving you is a logits mask, which means it is giving a probability matrix. Okay, when you pass in an image into a segmentation model, for every pixel, it gives you a probability value. Okay, now if this probability value is greater than 5, you make it white. If not, you make it 0. Okay, that is what is happening here. You understand, right? So then we could calculate, once we have the predicted mask, we could calculate the TPs, FPs, FN and FN. Again, this function is already implemented within the SMP package. It's called metrics, and get the stats. Now give the predicted mask, the ground truth mask, and it will return me all my TP, FP, FN and TN. Okay. Now from this, I can calculate my IOU score from the TP, FP and FN. From this, then what I am defining here is the training step. Okay, which means this, in this training steps, we have some common steps that is common for the training validation. So that is what has been defined in the shared step, and which is also reused in the validation. Okay. In training, what we do, we take a batch of training images, pass it through the model, get the outputs, and then append it to the training loss info, which we created here. Where is that? Okay, this is just a function. Let's see how we are using it uh, in the execution. So basically, we will create one for loop, which will iterate through the batches of data, and then we will keep appending this list here. Okay. Let's go to that for loop. Okay. Again, this is where the PyTorch Lightning comes. So what you have done here is you have done all the steps that needs to be used in your training routine. But the training routine, if you see in day 1, we implemented a for loop, which will load the training data batch by batch, and then it does epochs, right? That training routine is implemented for you by the PyTorch Lightning. So that is what this trainer module comes. Okay. So from the PyTorch Lightning, which is PL, you create a trainer object. Okay. And then you define the max epochs. And then here you have created the pet model. Within this pet model, you have defined all the train steps, validation steps, your loss functions and everything, and also your training parameters. Then you take this model, you take this trainer, and then start your training. which is basically trainer.fit, pass in your model that you created here, and then pass in the train data loader and the validation data loader. Now this trainer object, which is coming from the PyTorch lightning, will take care of all the iterations and the epochs. So it will load batches of data of every iteration, do the forward pass, calculate the losses, and then it will do the weight updation and all. Everything it will take care. So finally, after 10 epochs, we will have the training completed. So let's go and run this one by one. Now the training started. Okay. After training is completed, we validate the model using the validation data loader. This will give us evaluation metrics about the model's performance. Then you can then test the model on the test loader and then see if the model is accurately predicting all those maskers. That's it. Typical train validation testing loops. Okay. So here I'm skipping this Hugging Face thing, but if you want, if you have a Hugging Face account, probably you can also push these models from the collab notebook and then store it in your Hugging Face account. Okay, that's what they have shown here. Then some visualization. So after training of for 10 epochs, so this was my ground truth and this was my prediction. You can see still it is not perfect. Okay, if you train for more epochs, then this prediction will improve. You can see here this part is messed out completely. The tail part is messed out completely. Okay, so still they are not perfect. So the tails is not predicted properly here. Here the total head shape is distorted. Probably simple segmentations like this image where it is very clearly separated from the background, it is able to do a good job. But otherwise, some complex scenarios like this, it is completely failing. So which means 10 epochs is not enough. You can train it for more epochs. This is a very simple, like now you can go and use this notebook instead of pet data set, you can use it in your own data set. It's pretty easy.
That which equal is the first one. Equal which one is now in just
It's the epoch. Okay. Okay. So it download as an XML file. Yeah. 1 second, I'll just come back. So- It's okay. I think there is some. Yes. So whatever I exported, right, it came in an XML format. So what it says is your mask label has a polygon coordinates of this because I exported it into a CWAT format, but it could be possible to export it as a binary image, which I need to figure out. So, so this mask, right? Uh, School job data set. So uh, yeah, that's a good question. Like, I need to figure that out. So if you have a series of polygon coordinates, so instead of like for bounding box, we just have like x1, y1, x2, y2. But in this, you have like probably 20 coordinates, let's say, and each one has x1, y1. And then the predictor also have a similar 20 x1, y1. From this, there should be a way to identify what are the overlapping regions and what is the total area, and then we can calculate the ratio. That is already taken care within that SMP framework. But if you ask me how it is done by hand, that I need to understand a little more actually. Lois?
First, and then you see that we brought the mountain. That will convert into Excel. That makes it. And this will
See, for SMP, we need a binary mask, not XML. Binary mask. So if you see this image, right? Example of. So probably you can use this notebook as an example. I'll run this. So in this, there is a K-Wazir segmentation dataset, which is a polyps segmentation. So what it has is, it has images like this. Like this. So these are all medical images. Now you can see this one, right? This is like colon endoscopic image. So in this, you see there's a little bit polyps is there, right? They have to identify this automatically. This one, probably this one, and this one, all these things. Now, how can this one? So for this, what we have is, we have the mask in labels like this. This one, this is human labeled mask. So we use this, okay, to train a model that can predict those polyps regions within this image. Yes, to generate this mask, they use. Yeah. So we labeled right, but only thing is we need to figure out how to export it as a binary mask instead of XML. From XML also we can create a binary mask. Yes, of course. Yeah. So, see, that's why I demoed this SAM tool, right?
Each and every image. Meaning it must create.
Yeah.
What is trying to solve it? Why nobody is trying to solve it? Why nobody is trying to solve that problem?
Oh, for that only we have some little assistances there. So you're saying one button all should be labeled. So that's what there is a fundamental misunderstanding that ChatGPT was created automatically. ChatGPT was created on millions of labelers.
Has anybody created a tool which can do masking?
On its
LLM which can do create the masking.
It is based on our requirement.
No, I agree. Change. Is there any model which has been created?
There's a certain level of automations and assistance, but there's no any automation button that you click and all are labeled. And even if there is a guy says that, hey, I have a button that will label all your lakhs of images in one go, and I won't believe him. I mean, it's okay. He might generate, okay, but somebody has to go through all these images and check that the labels are correct. Otherwise, my model is corrupt.
Binary mask. So we have
So,
which masking is
so in this SMP, you just have to tell where is your images path and mask path. So here you see, right?
mask.
Huh? This one now. I have,
You have downloaded.
yeah, 1 second. I'll run this notebook for you.
Have some portion.
Okay, so this one. Okay.
Earlier you were saying not possible.
See, for this polyps image segmentation, see, this is the data set. He was here. So it has a images folder and a mask folder. Then it has a metadata.csv. It will tell you, okay, I have in this so many number of images, and it will tell you for each image, what is my image path and what is my mask path. Path, the full path, not just the file name. Yes. So then, because each image has different image dimension, no? Huh? That you can read an image and then get the height and width. This one you can create it programmatically, no? If I have a 100 image in this folder, and if I have 100 mask in this folder,
The same name.
yeah, I can create this CSV programmatically.
And the model, it takes the mask XML image or it takes the
Mask. My image overlay.
image overlay. There's some tool checking label me or something.
Yes, yes,
If
that
you
is
see that XML file, it will
Yes,
get
yes.
the images.
yes. So if CWAT is not able to give your XML, you can use label me kind of.
Label me.
Label me is there, like label another label G or something is there. Some one more nice tool is there. So those different types of tools you can use to create. Yeah. Yes. Image height and image width. Yeah. So,
In the properties, right? Property.
yes, yes, exactly. Yeah. So,
Segmentation.
yes, yes, yeah.
For object detection is not more easy.
Yeah. Because segmentation is needed for precise measurement of that cells. That's why. So then they will use that mask to measure that area in precisely in millimeters. Then they have medical limits. If your stone is of certain then it's okay. We can treat it in a different way. If it is of a beyond a certain size, then they treat it in a different way. Probably they will recommend you that, hey, go for a surgery.